Hello and welcome to G Fun Facts Online. Today we are diving deep into a technological revolution that is happening right now in the quiet, dust-free corridors of nanotechnology laboratories around the world. It is a revolution that makes no noise, yet it promises to echo through every single facet of modern technology. For the last 60 years, we have essentially lived in the age of the laser. Light amplification by stimulated emission of radiation. That technology transformed our world, giving us the internet backbone, precision surgery, and even the barcode scanners at your local grocery store. But light, for all its speed and brilliance, has a counterpart that has remained largely untamed until now: sound. We are talking about the Phonon laser, or the Saser. That stands for sound amplification by stimulated emission of radiation. For decades, the Phonon laser was just a theoretical curiosity. It was a physicist's toy that required temperatures near absolute zero and massive, room-sized optical pumps just to function. It was a scientific marvel, sure, but it was an engineering dead end. That narrative has now been shattered. We have effectively crossed a technological Rubicon with the development of the first electrically injected, microchip-scale Phonon laser. Imagine a device no larger than a grain of salt that emits a beam of sound so pure, so coherent, and so concentrated that it acts like a solid object. Imagine a beam of ultrasound so fine it can image the internal machinery of a single living cell without damaging it. Or a sensor so sensitive it can detect the mass of a single virus. Imagine your smartphone battery lasting a week because the energy-hungry radio filters have been replaced by a passive, microscopic sound wave generator. This is not science fiction. This is the dawn of the phononic age. In this episode, we are going to take a deep dive into the physics, the history, the breakthrough engineering, and the mind-bending applications of the Phonon laser. We will explore how engineers are literally trapping earthquakes on microchips, and how this silent technology is poised to be as transformative in the 21st century as the optical laser was in the 20th. To really understand the Phonon laser, we first have to unlearn our intuitive understanding of sound. To a human, sound is a messy, chaotic wave. It is a cacophony of frequencies spreading out in all directions, like ripples in a pond disturbed by a handful of gravel. But in the quantum world, sound is not just a wave, it is a particle. Just as light is composed of discrete packets of energy called photons, sound in a solid material is composed of discrete packets of vibrational energy called phonons. The sound we hear, a voice, a car horn, a musical instrument, is what we call incoherent. It consists of trillions of phonons acting independently, with different frequencies, different phases, and different directions. It is the acoustic equivalent of a standard light bulb, useful but diffuse and weak. A laser, the optical kind, works by forcing photons to march in lockstep. Through the process of stimulated emission, one photon triggers an atom to release a second photon that is an exact clone of the first. It has the same frequency, same phase, and same direction. This cloning process cascades, creating a coherent beam of light that can travel vast distances without spreading. A Phonon laser does the exact same thing, but with vibrations. It forces the atomic lattice of a material to vibrate in perfect unison. Instead of a chaotic jumble of jitters, the atoms move in a synchronized choreographic wave. This is coherent sound. Now, you might ask, why bother making a laser out of sound when we already have lasers made of light? The answer lies in the fundamental relationship between speed, frequency, and wavelength. Light travels incredibly fast, at 300 million meters per second. Sound in a solid travels much slower, roughly 3,000 to 12,000 meters per second. Because sound is so much slower, a sound wave at a specific frequency has a much shorter wavelength than a light wave at the same frequency. Let me give you a concrete example. A standard Wi-Fi signal operates at 2.4 GHz. As an electromagnetic wave, its wavelength is about 12.5 centimeters. But if you convert that 2.4 GHz signal into a sound wave traveling through silicon, the wavelength shrinks to a few micrometers. This compression is the killer feature of phononics. It allows us to manipulate information and build devices that are thousands of times smaller than their photonic counterparts. It also allows us to image objects, like the internal structures of cells, that are invisible to optical light due to diffraction limits. The concept of the Phonon laser is almost as old as the optical laser itself. In the early 1960s, shortly after Theodore Maiman fired the first ruby laser, physicists began to speculate if the same principles could apply to acoustic waves. However, the Saser faced a massive thermodynamic hurdle: the heat problem. In an optical laser, you pump energy into atoms to excite their electrons. When they relax, they emit photons. In a solid, however, relaxing atoms usually just jiggle randomly. They create heat, which is just incoherent phonons, rather than coherent sound. For decades, trying to make a Phonon laser was like trying to whisper a symphony in the middle of a screaming crowd. The thermal noise overwhelmed any coherent signal. The first successful demonstrations of phonon lasing required extreme measures to kill this thermal noise. There were the gallium arsenide superlattices experiments in the 2000s, notably by groups at the University of Nottingham. They used stacks of ultra-thin atomic layers. By firing electrons through these stacks, they could generate coherent phonons, but only at temperatures near absolute zero. Then there was the optomechanical approach, with breakthroughs from the Valhalla group at Caltech. They used tiny silica discs, or rings, and pumped them with intense optical laser light. The pressure of the light physically shook the device, creating sound waves. If the optical feedback loop was just right, the sound waves would amplify. This was a phonon laser, but it was essentially a parasite on a massive optical laser setup. It wasn't a standalone device you could put in a phone. These early devices were brilliant physics experiments, proving that sound could be coherent. But they were not engineering solutions. They were bulky, required liquid helium cooling, or needed powerful external lasers to function. The game changed fundamentally in the mid-2020s. The holy grail was always an electrically injected phonon laser, a device that you could hook up to a battery, just like a laser pointer, and get coherent sound out. This was finally achieved through a collaboration involving the University of Colorado Boulder, the University of Arizona, and Sandia National Laboratories. Their device, published in Nature in early 2026, represents the transition of the phonon laser from physics experiment to engineering component. This breakthrough device is a hybrid integration of two distinct materials, each chosen for a specific superpower. First, indium gallium arsenide, a semiconductor famous for its high electron mobility. This is the engine of the device. Second, lithium niobate, a piezoelectric material, meaning it can convert electricity into mechanical strain, and vice versa. This is the body of the device. The operating principle of this new microchip laser relies on a phenomenon called acousto-electric amplification, which works on a principle similar to a sonic boom. Here's how it works. A simple DC voltage is applied to the indium gallium arsenide layer, causing electrons to flow. As the voltage increases, the electrons move faster. Eventually, their drift velocity exceeds the speed of sound in the material. When electrons move faster than the sound waves they are traveling with, they begin to surf the sound waves. Instead of colliding and losing energy to resistance, the faster electrons transfer their kinetic energy into the sound wave. This energy transfer amplifies the sound wave. A tiny thermal vibration creates a sound wave. The supersonic electrons feed it energy, making it stronger. The wave reflects off the ends of the chip, passing back through the electron stream to get amplified again. The result is a self-sustaining, highly coherent acoustic wave trapped on the surface of the chip, a surface acoustic wave. The researchers described it as an earthquake on a chip. But unlike a chaotic earthquake, this is a controlled, single-frequency seismic event occurring at gigahertz frequencies. Crucially, this device operates efficiently. It doesn't need a massive optical laser to pump it. It doesn't need near-zero temperatures, although thermal management is still key. It is a true sound diode. This specific breakthrough bridged the gap between the science of phonon lasers and the industry of semiconductor manufacturing. It proved that we can build phonon lasers using the same tools and materials used to build computer chips. While the chip-scale laser is driving industrial excitement, another type of phonon laser is pushing the boundaries of fundamental physics: the levitated nanoparticle phonon laser. Imagine a tiny glass bead, only 100 nanometers wide, floating in a vacuum chamber, held in place not by wires, but by a focused beam of light, an optical tweezer. This bead vibrates naturally due to thermal energy. By monitoring its position with a laser and applying an electronic feedback loop, physicists can either dampen this motion or amplify it. When the amplification overcomes the natural damping of the vacuum, the bead's motion shifts. It stops jiggling randomly and starts oscillating in a perfect, high-amplitude sine wave. The bead itself becomes the phonon laser. These levitated systems are not designed for smartphones. They are the ultimate sensors. Because the bead is floating in a vacuum, it is disconnected from the physical world. It has almost zero friction. A passing gravitational wave, a tiny fluctuation in the electromagnetic vacuum, or even the gravitational pull of a nearby microscopic mass can disturb the bead's perfect rhythm. These systems are being used to test the limits of quantum mechanics, exploring if a large object like a 100-nanometer sphere can be put into a superposition state, vibrating and not vibrating at the same time. So we have the technology, we have the chip-scale devices, and the high-precision levitated systems. What do we do with them? The applications range from the mundane to the miraculous. First, the wireless revolution. Your smartphone is packed with filters, components that block out noise so your phone can tune into the specific frequency of 5G, Wi-Fi, or Bluetooth. Currently, these are surface acoustic wave filters, but they are passive. They eat up signal strength. They are bulky. The phonon laser changes this. An active SAW device, one that amplifies the signal rather than just filtering it, could replace dozens of passive components. Because the phonon laser emits such a pure tone, it acts as an incredibly sharp filter, allowing for tighter packing of radio channels and more bandwidth. Plus, by changing the voltage, the frequency can be tuned. A single chip could theoretically handle Wi-Fi, 5G, and GPS frequencies dynamically. Then there is medical imaging, phonon microscopy. This is perhaps the most visually arresting application. Optical microscopes are limited by the diffraction limit of light. Electron microscopes can see smaller, but they often kill the sample. Sound waves at gigahertz frequencies have wavelengths comparable to ultraviolet light, but they interact with matter completely differently. Light interacts with chemistry. Sound interacts with mechanics, stiffness, density, elasticity. A phonon laser beam can be focused to a spot size of submicrometers. When this beam scans a living cell, the nucleus reflects sound differently than the cytoplasm because it is stiffer. Fat droplets and tumor cells have distinct elastic properties. Phonon microscopy allows us to take ultrasound images of individual cells in 3D. We can watch a cell divide or watch a drug molecule stiffen a cell wall in real time without using toxic dyes. Moving to the macro scale, we have deep earth and infrastructure scanning. Coherent acoustic sources could revolutionize geological surveys. Instead of using explosives to generate noisy seismic waves for oil and gas exploration, a coherent acoustic source could provide laser-sharp images of underground reservoirs. Similarly, embedding phonon laser sources into bridges or pipelines could allow for continuous monitoring of cracks, detecting interference patterns caused by microscopic stress fractures long before they become visible to the eye. And finally, the quantum transducer. In the race to build a quantum computer, we have a connectivity problem. Superconducting quantum processors operate at microwave frequencies. Quantum communication networks operate at optical frequencies. They do not talk to each other easily. The phonon is the perfect diplomat. A gigahertz phonon has an energy that matches superconducting qubits, but it can also be coupled to light via optomechanical crystals. The phonon laser can accept a quantum state from a processor, convert it into a coherent phonon state, and then transfer that state onto a photon for transmission. Despite the triumph of the earthquake on a chip, significant hurdles remain. First, the thermal death. Heat is incoherent vibration. Operating a high-power phonon laser generates heat, which immediately tries to destroy the coherence the laser is creating. Innovative cooling strategies are essential. Second, frequency limits. Pushing this to the terahertz range requires features to be fabricated at the nanometer scale. If the chip surface isn't atomically smooth, the high-frequency sound waves scatter and die. And third, integration. Putting exotic materials like indium gallium arsenide and lithium niobate onto standard silicon chips is tricky. Foundries are hesitant to contaminate their production lines, so developing CMOS-compatible phonon lasers is a major area of research. Looking ahead, we are standing at the threshold of phononics. The vision is the phononic integrated circuit. Imagine a single chip where computation is done by electrons, communication is done by photons, and signal processing and sensing is done by phonons. In this architecture, the phonon laser is the beating heart. We may soon see lab-on-a-chip devices where a phonon laser acts as an acoustic tweezer to trap a blood cell, an acoustic microscope to image it, and an acoustic sensor to analyze it, all on a disposable chip costing a few dollars. The optical laser began as a solution looking for a problem and ended up rewriting civilization. The phonon laser is currently in that exciting adolescent phase. We have proven the physics, we have built the first practical engines. Now the creative explosion begins. From the silent microscopic earthquakes on our chips to the levitating spheres probing the quantum void, the 21st century will not just be the age of light, it will be the age of coherent sound.